Yeah, potentially. There's other positions here. I mean, we have plenty of former CS students who work at the university who aren't teachers. They work in IT or some other capacity here on campus dealing with technology. The trade-off is, I mean, it's not like the pay is nothing, but the pay is probably going to be 20% less than you would get outside, but it ends up being a vocational type. I mean, I think there's something nice about working for a, yeah, I mean, it's, you know, not all, you know, it still has this nasty underbelly like any other place, but there's a lot more right about it than wrong about it. So you know, but then you can go get your side gig. And we have a former student who has a t-shirt business. Fascinating, actually. He's come back to some of the hackathons. His name's Shiva, and he married an American girl, and she's an accountant and he's a software engineer. So he works, makes good money, but they started this like side t-shirt business, and they also have mugs and stuff where they have like little sayings, things like that. And you think like, okay, that seems like stupid. They make like legitimate money, 4 or 5 grand a month, just like spending 10 hours a week coming up with like the saying of the week, you know, like whatever's in the news. You know, I'm sure they had mugs dealing with like Black Lives Matter, and they probably had stuff dealing with COVID for some of the different hot topics that come out every other week. You know, whatever it is, they take whatever's in the news and they come up with some sort of thing that people want to buy. And then they sell it and they use other people, you know, to fulfill the shirts and stuff. So they're not making the mugs or anything. They just come up with sayings. Shocking. So I make them buy dinner every single time we meet up. Well, I'm a pauper. I'm a professor at a Christian school. I don't make anything. Oh, I was nothing. Yeah, the company's made a couple of bucks. Let's see. I tried to retire at 37. It didn't stick. I got, yeah, I was bored. Yeah, I don't need any more money, but you got to have something to keep yourself mentally rolling. Okay, so we were doing Boolean expressions for today. So creating a language of Boolean expressions. Last time we made a language of functions, very simplified language with one production. And now we were adding, did I specify? All right, Boolean expression, arithmetic Boolean expression. So we have our the normal dealy flippy thingies. All right, so let's go and write our parser for this. I'm going to go ahead and actually just give ourselves a slide so we can flesh out the where's Jason today? Oh, it seems so nice and peaceful in here. That's it. I think I see him online. All right, so we have less than, greater than, less than or equal to, greater than or equal to, then maybe what, not equal to? I said equal to, didn't I? At least I thought I did. Now we can decide, actually, you see this in some older languages. I don't know if you've worked with a language before, but like instead of the less than sign like that, their operator will be LT, less than. I'm just saying it exists. We can do whatever we want, but it's kind of evidence of this building process where the designers of a language get to decide what symbols or what syntax do I want to use for different things. So you will find some languages that do use like LT and GT and GTE for greater than or equal to for those things. But it sounds like you want to use the normal mathy things. Do you ever get answers to it? If you get answers to it and you have the question again, it seems like it's a waste of time to keep asking it. All right, I'll answer it. Go ahead.
Is there a language that forms scheme? That sets the scheme?
No, I mean, scheme was just born out of nothingness.
Okay.
Yeah, it's in first couple books of the Bible. In the beginning, it's like it's left out a couple of them with this is mate scheme. Well, yeah, but I mean, you could write a scheme interpreter in Scheme, but really what you're asking is where did it originally come from? Yeah. Somebody wrote something ahead of time. Well, Scheme is a superset of a language called Lisp, which has all the cars and cutters and stuff. Realistically speaking, the first Lisp interpreter was probably written in C. And then the first C compiler was written in assembly. And so you roll back to become less and less friendly to humans, which is why we're looking at interpreted languages in here, because this is actually friendly to humans, right? So F is for French, of course, based on our previous comment. French to Russian, haha. Gotta keep up. But yeah, so I mean, that's, so at some level, all these languages were written in assembly. And then what came before assembly? Well, well, possibly, human beings, we had to create the idea of binary being the thing that backs up assembly, but you would have had to write, like when the 450 class, we talk about bootstrapping. So if like you're writing your own operating system, how do you get from the system BIOS, the little chip that's on your motherboard that starts your computer up and hands it off to the next step, the operating system that lives in the master boot record of your hard drive, which then passes it off to the next step. How do we go from effectively nothingness? You're going to have some sort of starting point, even if it's built in hardware, that allows you to start that initial handoff. But typically, the closer you are to the beginning, the less human friendly it is. But no, the answer to your question is this: nothing made Scheme. Well, God made Scheme. It was just created. So ask Pastor Smith about it. That's true. And the closer you get to it, the less capable we are of doing the same thing. So it's that same answer you get from Pastor Smith. Now you just saved yourself a trip. All right. So does this cover all the stuff we're going to do for arithmetic Boolean expressions? So let's build. We're going to have our parser and our interpreter for Boolean expressions. It's going to cover all of our Boolean expressions. Because if you think about the uses of Boolean expressions, like for instance, in conditionals, a conditional is usually going to be if some Boolean expression. And now that Boolean expression is any expression that boils down to a single value of true or false, right? So that can be one of our arithmetic Boolean expressions, or in the future, maybe one of our logical Boolean expressions with ands and ors and that kind of jazz. Make sense? We don't want to have in our language that it's an if followed by an arithmetic Boolean expression or a logical Boolean expression. It's a Boolean expression. And Boolean expressions come in a couple of different flavors. All right, so where's my parsers? Parsers are up here. So we'll define Boolean expression parser. And this guy will take in a Boolean expression. going to be a lambda that takes in a Boolean expression. We're going to have a cond. All right, and now we're interested. Our Boolean expressions come in one of these flavors. So we can decide which dude it is by the car of it, right? All right. So the car of this guy is going to be either a less than or equal to, a greater than, equal to. So cond EQ car Boolean expression, that guy's equal to less than. Then we want to build a parsed version of this guy. So maybe what we do is we represent the parsed version with more like verbiage. So maybe we use the phrase less than or something like that, how we want to store it in a parsed format. So maybe our output here is going to be a list containing, we can say LT or so less than or less than. Or do we just put both. Which is the correct way to begin with? EN? All right, we'll roll with it. If it's wrong, it's Emily's fault. All right, so we'll create a list out of less than. Now, the next two parts are no lang expressions. What do we do with no lang expressions? Call parse no lang expression, or call parse on what no code expression. So that's no parser, right? So it's less than followed by the result of no parser on the car of the cooter of our Boolean expression, and no parser on the car of the cooter. Like that, right? So that handles if we're looking at a, we need to go one more here. That handles if we're looking at a less than. Then we just repeat that. So this will be less than or equal to. This will be greater than. This will be greater than or equal to. This will be equal. And this will be not equal. Actually, put an else. Not a valid Boolean expression, like that. Make sure it's okay with that. Do I have to put those in that in. That guy. Okay. All right, so that should be our parser for this dude, right? And we can test this quickly. So let's do less than. Five, 2, something like that. And that should give us a parsed version of that with 2 numlet expressions. Less than or equal to. Greater than. Greater than or equal to. Oh, did I not put a greater than or equal to? Greater than, I didn't. Less than, oh, I didn't change. Less than or equal to, greater than or equal to. There we go. Equal to. And then not equal to. All right, so that's our parser for our Boolean language of Boolean expressions. We're good with that. All right, so now we want to write the interpreter for that guy. This is going to be our define run parsed Boolean code. This is going to be a lambda. It's going to take in some parsed Boolean code and an environment. Okay, put that down a little bit. All right, now for run parsed Boolean code, we need to ask ourselves, well, what would we do with this? So if I'm looking at this is Boolean code here, right? If I'm looking at something like that, what do I actually want to perform as a relation relative to this? Remember, the Boolean expression is any expression that boils down to a single value of true or false. Go ahead. Okay, or I could return true or false. Yeah, I don't have to invent my own. I mean, because ultimately this is the interpreter part of it, right? So this guy is a parsed Boolean expression. My job for running a Boolean expression is to produce a true or false, right? That's what a Boolean expression does. Boils down to a single value of true or false. Keeping in mind that somebody else is going to give me the answer for this guy. Somebody else is going to give me the answer for this guy. I'm going to call, who knows how to give me the answer to this guy? If I have this parsed code sitting in front of me, who knows how to give me the results of that expression? Yeah, run parse code. Because that guy is in a different language, but we have an interpreter for that language. So in this interpreter, I'm going to say, oh, I'm looking at a not equal. Fine. Who are the dudes that I'm determining if they're equal or not? So we're going to call run parse code on this dude and get an answer. Run parse code on this dude and get an answer. And then I'll determine, are those two answers not equal to each other? If they're not, I'm going to return a true. Right? If they are equal to each other, I'm going to return a false. That's what this interpreter is going to do. It's not, presumably, we're going to be running this code someplace else another time, depending on the position in which we're doing it. All this guy's job is to handle the Boolean expression part of it. Boolean expressions boil down to true or false. That's what this interpreter does. It's a language whose result is always either a true or a false. All right, so we'll have our cond set up here. Equal car parse Boolean code. And we're going to introduce something new today that'll make this guy easier. Okay, so, but I'm going to write it the way I would have expected you to write it first, and then we'll upgrade it to the newer cool kid way. And just for Jason, this is going to involve 4 nested maps. Did he just log off? I was hoping. It's not going to be maps. We're going to look at let expressions, which will clean this up quite a bit, what you'll see, because we're going to have a lot of duplication, just like we kind of had before. All right, so if we're looking at a car parsed Boolean code, and this guy is equal to less than, where you're looking at that dude, then I want to boil down to less than the result of calling the built-in less than function on whatever run parse code returns on the catter of parse Boolean code I'm going to kick this down the line, along with whatever run parse code returns for the cadder of run parse code. Keeping in mind that this is the car, this is the cadder, this is the cadder. Two Ds. All right, so that's what we're doing. We're extracting these individual pieces. That's what the car, the cadder, the CADD are. Except this piece I call run parse code on. This piece I call run parse code on. But run parse code requires me to give it the current environment in order to work, which this interpreter did take in as a parameter. Because run parse code takes parse code and an environment in order to do its job. So this guy right here is going to boil down to presumably a numeric value, right? An answer from running that parse code. This guy is going to presumably boil down to a numeric value, something that it would make sense to apply the less than operation to. And we're just going to boil down to whatever this guy returns. I don't have to ask. If it boils down to true, return true. If it boils down to false, return false. I could just return or boil down to whatever it boils down to. Make sense? All right, now I'm going to repeat this for every single one of our guys. Oh, hold on. I zigged when I should have zagged. There we go. So that's going to be less than or equal. Greater than. Greater than or equal. equal. Notice here, this really drives home the idea that we are assuming that the result here is going to be a numeric. We're effectively building primitive Boolean operators. So we think back to a language like Java or something like that. This is equivalent to our double equal sign in Java, which compares numbers, primitive types, not just numbers, but numbers, chars, pointers, but not what the pointers point to, but the memory addresses themselves, those types of things. It won't work for like comparing strings, which don't exist in our language yet either. But we would presumably, when we add object-orientedness to our language, we'll presumably have to have a way of comparing objects to each other at some sort of default way, and we'll talk about that when we get to it. But our assumption is these are the primitive Boolean operators. All right. So really mimicking what we have in our pretty much every language you've been introduced to. Although I guess in let's see, this group had Python in their 200 class. So in Python, technically the double equal sign does work for strings because they've overridden that operator to function for strings. But in Java, when you try to compare strings, it's actually comparing the memory address under the hood, not the contents of the string. So this mimics what we should already be used to. So equal, I'm going to return equal there. Not equal. I think this guy is going to be not. Let's just go back to that guy there. That would be the not of that. There might be a not equal operator. Nope. So it's going to need to be not equal 5, 4. 5 and 4 are not equal to each other, so this should boil down to true. Okay. And then we could throw our else in here. Not a legal Boolean expression. All right, so that'll run some parsed Boolean code. Less than or equal to, greater than equal to, equal to, not equal, and then less than or equal, greater than or equal, equal, not equal. Does that match up to what's thrown up here? Less than or equal, greater than or equal, equal, not equal. Looks like it matches up. All right, so let's test this on a simple example with like an if statement. So we'll go down here. Let's update our we do need to update our if statement now, right? Because right now our if statement makes the assumption that we're asking, is it equal to 1 or not? The catter of our parse no code presumably is a Boolean expression. I remember last time we were deciding whether it was going to be the CAADR or just the CADR, whether we were going to bring it in as a parenthesis inside the parentheses or by itself. So we can, I think right now it'll be we want the entire thing because that will be our parse no code or our parsed Boolean expression. So when we get to this if statement here, we want to ask the question, if something is true, if what is true, if our Boolean expression, and let's go ahead and let's write some code so we can see what this is going to look like. So we're going to say if open parenthesis less than B5, let's say, then boil down the one, otherwise boil, let's see, what's my syntax for if? Should be able to look at my reference too. Let's just look at my code reference here. Oh, ask. Ask. This guy now gets updated to a Boolean expression. No language expression, otherwise no language expression. Okay, so my Boolean expression lives inside of these parentheses here. So we do need to make sure that our parser, or this guy, our parser for no code, knows how to call upon our parser for our Boolean expressions so we get the right code out of here. So let's go up to our no parser. Right now, when our no parser is looking at an ask, right here, it has our ask expression. It's creating an ask expression as the parse version. And then it's just including the 1 or the 0, the CAADR. That's the contents of those parentheses. Okay. Now we can go back in here and we can say, well, now that we actually have things that are Boolean expressions, this parenthesis is no longer really part of the syntax because the Boolean expression is already enclosed in parentheses, right? We can certainly have an extra layer of parentheses if we want. So we can have ask parentheses, and then inside anything that's a Boolean expression, including things that already have parentheses around them that we should run. So we can decide what we want to do. I would say that we could probably go ahead and not assume there's an extra layer of parentheses and say that the correct way to ask a question is to ask the question and then either do something, otherwise do something else. One of those two things. All right. So that means we'll create our ask question. It is the car of the cooter of that no code that will be our unparsed at this point in time Boolean expression. And what do we do with an unparsed Boolean expression? We call Boolean expression parser on it. So we'll call Boolean expression parser on this unparsed Boolean expression, which is the car of the cooter of an ask expression. Right here, the car of the cooter is our Boolean expression. And we need to parse that, so we pass it over to our parser for Boolean expressions. All right, make sense? All right, so that should put it all in the right format for us. So that's the upgraded version of just assuming a 0 or a 1 for before in our parser. We just passed it along. We didn't do any parsing of a 0 or 1. We just said, look, it's good as is. Now we've added the ability to ask legitimate Boolean, create legitimate Boolean expressions. So then our parser, or in our interpreter rather, when we're running ask expressions, go ahead. Possibly. For no parser? Well, but this is for call expressions. Oh, these guys. ask expression. Well, no. Because the Boolean expression itself has the question we're asking. These guys are the things that we should do if it's true or false. Yeah, but I mean, it's a good question because I can see how that could be confusing. When you think about an if statement, we're saying, if something is true, do this, else do something else. Yes, we are asking part one and part two of the if something is true. We're applying the Boolean operator to two things, but then we have other things that need to happen. And we need to parse those because depending on the run of our program, if you think about the assembly under the hood here, we will branch to one of these two sections of our code. And we need to have that as our final program because if a variable value changes, then we might do the otherwise, or we might do the normal if true part. Go ahead. I don't think you can do that at the time of the parser. The time of the parser, we don't have the environment. So even if we look at just a simple case of a var expression, we don't know what the value of a variable a is going to be. So we don't necessarily know which one we have to give them. Yeah, so, but that wouldn't be, it wouldn't be runtime efficiency in an interpreter. I guess it would be because we would be outputting less. But so then I go back to my first answer. We don't have enough information to make that call here. So we have to provide him both options so that during runtime, it can choose the right path. What he wanted to do is, it's like, look, I only want to give you one or the other for the executables, depending on the result of the Boolean expression. And this really comes down to the difference between a parser and an interpreter. Parsers pre-format code, interpreters actually run it. So even if we did, I would even make the argument, even if we did have the information to make the decision right now, we probably shouldn't based on the definition of what a parser's job is and what an interpreter's job is. All right. So I think this is good as is. And if there's a bug in there, I did it on purpose. Hold on, I'm lost. What am I doing? That's my run parse Boolean code. Let's get to my run parsed code. All right, right here. So if I'm looking at an ask expression, I'm no longer just checking to see if it's equal to 1. Now I actually need to call my run parsed Boolean expression or run parsed Boolean code. Right here, I'm not just checking this. Now I'm going to call run parsed Boolean code on the catter of parse no code. Passing it my environment. Keeping in mind that the catter will be like this piece here, or if you want to see it in this format, this is the catter of our parsed Boolean expression. It's the part, or the catter of our parsed no code will be the parsed Boolean expression. And what do we do with parsed Boolean expressions? We pass it to the dude who knows how to run parsed Boolean expressions, which is run Boolean expression. Make sense? All right, so we'll run this guy. And what should the result of run parsed Boolean code always be? One of two things. Go ahead. True or false. Is running a Boolean expression. Boolean expressions are any expression that boils down to a single value of true or false. So presumably, if we call our interpreter to interpret a Boolean expression, he's going to give us a true or false. That's his job. Because it's something else other than true or false, We wrote bad code, and I did it on purpose. Well, actually, hold on. Here's the caveat. This is the haha coding caveat. Technically, if he gives you something other than true false, not a legal Boolean expression, that means that you wrote bad code. Your no code is improperly formatted. Make sense? Which more times than not, since we're inventing this language on the fly, we're probably actually more prone to write bad syntax in our newly invented language than we are at writing bad syntax in Scheme. We'll forget the word otherwise or something like that. But then it's your fault since you're inventing the language. Well, I mean, it's equivalent to, he's doing his homework. He's looking up the French in a Spanish dictionary. And the problem is it's not any worse. Like, look, this is just as good. Do you know Spanish?
Very little to the point that it fits.
Oh, yeah. I had what, 3 semesters of Spanish, and my joke is I know enough to order at Taco Bell. My wife had like years of Spanish, and she won some like Illinois State Award for like, I don't know, honorary Spaniard or something. And she can't even order at Taco Bell. She can read it and write it, but she can't. Yeah, she can't speak it very well, and she definitely can't understand it. So, was there a question unrelated to Spanish? All right, let's keep rolling here. All right, so this would be the one circumstance where our run Boolean code would give us something other than true false, and that's because you gave it bad parsed code. All right, but otherwise, the job of our run parse Boolean code is to ultimately, this guy should produce a true or false. So then we can say, if this boils down to true, do this. Otherwise, do this. Make sense? Instead of what we had before, where we just said, if it's equal to a 1, do this stuff. Otherwise, do the other stuff. So he just upgraded this thing. All right, so here's our sample no code. So already I have bad syntax, right? Because this should be ask less than B5, 1, otherwise 2. And if I wanted to, I could turn that into a B or something like that, which should be a 5. Actually, let's make it a C. So if B is less than 5, which it currently isn't, this is going to boil on a C, which is a 23. So there's our 23. If I say unless they're equal to 5, now it should give us a 1. There's our 1. So obviously I didn't give you any on purpose mistakes this time. Until we find a bug later on. Actually, for thoroughness, we probably should go through and check them all. B is greater than 5. This should give us the 23. I don't think we need to check this side. I think we've pretty thoroughly checked our run no code stuff, but we really want to check the new stuff we put in there. So if B is greater than 5, which it's not, we should get a 23 out of this. Greater than or equal to 5, which it is, we should get a 1. Equal to 5, which it is, we'll get a 1. Not equal to 5, which it's not, we should get a 23. All right, where did that go wrong with mine? Well, first of all, did I write it correctly? This is what not equals is in our language, right? Okay. betting it's a parenthesis issue here. Not equal to that guy. That's in and of itself. That's in and of itself. That checks if they're equal to each other. This inverts that to not equal. That closes that. That closes that. I think that's okay. Let me look at the parse no code on that guy real quick. Ask not equal var expression b lit expression 5. That looks good. Okay. Use the word not equal. Let me just copy that in case I have a spelling error up here. So our run parse Boolean code is equal to not equal. That looks correct to me. The car is equal to not equal, which it would be. Then we're going to call this guy. We'll call that guy. We'll check to see if they're equal to each other, and then we'll invert it. Oh, I have an extra parenthesis there. There's our 23. Okay. I think we checked all the Boolean operators now. All right, so that was the homework, right? Is that everything I asked you to do? Let's see. Grammar.
Excellent.
Oh, did I not have the oh, here, homework is to implement the arithmetic Boolean expression into its own parser and interpreter and expand ask expression to support these. Okay, so I think that's our homework, right? All right, so questions about that. I'll copy that code, put it up here on Slack. Well, then let's handle this question about fall break before we go on. Oops. Code that supports arithmetic Boolean expressions. All right, so when is fall break? For 22nd. So that means we could do the midterm on the 19th if we did it beforehand. Yeah, I'm fine with that. I think that's probably preferred, not just for the rationale of, you know, hey, that way we can go and have a good vacation, not have to study or anything during it, but also from the perspective of retaining information, because typically when you go away, everything that has been stuffed in there for a while starts leaking. It is. So let's say midterm will be October 19th. I haven't decided yet. Remind me on the what's the Thursday before that? 15th? 14th. So remind me on the 14th, and I'll go through the slides and review for it. And then we'll talk about logistics for taking it. I think the answer is probably, and that's not even like my choice. It's always like something ends up happening with somebody's computer, and it's just easier if I say you have to finish it in one sitting, but get it in by midnight or something. And with that in mind, I may, not that I'm promoting this, but I may actually put it up like maybe Sunday night or Monday morning and just say you have to have it in, before midnight on Tuesday or something. Because I know sometimes, not that any of you would do this, but you leave for vacations a little bit early. so let's say that's likely. So remind me of all that on the 14th, and we'll review for it and stuff. Sound good? All right. So I did promise that I was going to show you a better way of doing a couple of these things, and this involves I think it's 4, maybe 5 maps. So we're going to look at stuff called let expressions. So we're learning about a new tool in Scheme. So creating local environments. So we actually have 3 versions of these. We have a let star, and a let rec. All right. Let rec. I really wish there was a way to like just turn off autocomplete on Keynote. Like I appreciate it trying to correct my spelling under a lot of circumstances, but maybe not. She's Googling it. There probably is like an obvious. It's like, why didn't you ever Google it? I think I did. I think I did Google it at some point. Yeah, but Apple made this. If you're not using it the Apple way, you're not using it at all. So, and that's coming from me. I'm a Mac user, but that's been my experiences. Microsoft software typically oversolves problems, and Apple software typically undersolves problems. They do exactly what they intended for you to do, no more, no less. Even though the user sometimes might want to stretch it. Where take a product like Excel is a good example. Excel does about 4 billion things, and 99.9% of human beings only need about 60 of them. And really 98.9% of humans only need 10 of them. But the point is that those other features are there if you need them, because it's been a buildup over the years. Where numbers, the Apple equivalent to Excel, is significantly less capable, but I would say meets that 99% of all users quota. I prefer numbers just because I'm not a power Excel user, but
I would expect the exact opposite, but that kind of makes sense.
why?
Well, Apple being premium. Do you think they would,
Well, premium, but only if you agree with their way of life. And again, I mean, I'm an Apple user, but when you walk into an Apple store, I look around for where the Kool-Aid is. It has a feel. You walk into a Microsoft store, not that they really exist. I think that was a mistake for the Microsoft stores, but you just have a different, it's just different. But we kind of need them both, because that competition creates the, maybe we call it animosity, but we see it in our iPhone users versus Android users. My wife's an iPhone user. I was an iPhone user for years. I'm an Android user now because I write software for both. But a couple of things Android lets me do that I can't do it on iPhone. I think I've said before, it lets me share a Wi-Fi connection through my Wi-Fi, where the hotspot on iPhone only lets you share a cellular connection through your Wi-Fi. Well, that's a deal breaker for me. We go on a lot of cruises, and it's beneficial for me to share the Wi-Fi I'm connected to with my phone with the Wi-Fi on my laptop. One feature, not that I don't, there's other things that I use it for, but that iPhone also can't do, but you know, that's just an example. I think I've said it in one of your classes before. Yeah. It's the same things before. You say you ask the question and you get the answer, you don't remember the answer. So you ask it again later on, just wasting everybody's time.
Yeah. And then you tell me this stuff.
I didn't say it this time. I thought it was implied. I'm glad you're at least remembering that aspect.
I will.
I had a funny conversation with Dr. Wall yesterday after you walked away from our table in the cafeteria. He goes, I don't think you realized you were joking. I said, I hope not.
No, I realize.
I know. But the point is, I don't care if you did or not. Yeah, I get enjoyment out of the aftermath of the conversation either way. But he seemed to be bothered by it. Because he's a much nicer person than me. That's actually probably not true. We're both pretty nice people, but he's a little bit, yeah, he's less rough edges until you get to know him. As President Cario once said, I'm an acquired taste. I go to church with the guy, so, and him and I are pretty good friends, but I am an acquired taste. All right, so creating local environments, let versus let star versus let rec. These all solve the identical problem, but we're going to show some of the weaknesses of them. So let's look at a syntax for a let first. So we have a let, and it is lowercase, but just let me roll with it. Then we have some opening parentheses, and this is going to be two lists of name value pairs, followed by the body. What you want to happen in this new local environment. So let's look at this through an example. I'll just not run our parse code here for a second. All right, so I'm going to just do, I'll define let sample to be a lambda. Actually, I don't need to take in anything. We're just focusing on the let aspect of it. All right. And this guy is going to create a let. And there's my parameter list. There's my variable, my local environment that's only in existence while this let works. So inside here, I'll say A is 1, B is 2, C is 3. Something like that. So I just create a list of two lists. Those guys being variables that I now have access to only inside the body of this let. As soon as this let's done, those variables disappear. Okay, so now I can do something like plus A plus, all right, let's see, times B, C. So B times C is 6 plus A is 7. So this guy should boil down to 7. So there's my 7. All right, so this stuff right there, that is the body of that local environment, the let. These are the new variables that were created in that local environment. Now I'm going to go ahead and I'll throw another variable D in here. So this is a variable that came into the function. So let's say D is what we're going to add there. So we'll say let sample, we'll do a 2 here. So when I call let sample, I'm passing it a 2 for D. I'm now creating a more local environment that has an A, B, and C variable defined. And I'm saying D plus B times C. I still have access to that variable D inside of here because variables resolve to their most local definition. It first checks this more local variable scope, doesn't find a D in there, bounces up and says, ah, I found it bound there. So this is going to give me an 8. All right, so this doesn't replace the more global environment, but it does give you a more local environment. But what if I change this to A and A? So inside here, A is 1, up here, A is 2. I get a 7. So we're seeing that this, again, all variables resolve to their most local definition. A is defined here, but A is also defined here. But since I'm using A inside the body of the let, it boils down to the most local definition of A, which is 1. So we would say that this version of A shadows the more global version of A. That makes sense? Go ahead. No, let in JavaScript is for variable definition. Yeah. For single variable definition, it's just defining here. So let something be something and then do this. Actually, there is a body to that. Call it loosely related. I think that's fair. All right. Now weakness. Actually, I can do it this way. All right, so notice I've changed my let. I'm saying A equals 1, B equals 2, and C is equal to B. And it's screaming at me. It's saying, hey, I've never heard of a variable named B. Now in our head, we're saying, well, it's right here. The normal let does not allow you to define variables in terms of the other variables that are defined in there. I now need to use the let star to accomplish that. Now he's okay with it. But notice it still goes left to right. So I'm trying to set B equal to C here, but I haven't actually defined C yet. So you still need to have the variables defined inside of the let star prior to using them, even during the variable definition. All right. And then so it should give me a 4. There's my 4. All right, so this one at a glance should look a little funky. The value of C is a lambda expression. Well, what can I do with lambda expressions? Well, I can call a function on a parameter. So I'm passing 2 in for x and multiplying them together. Well, multiplying the x by 2. Okay, so I can store a lambda as the value associated with the variable. And that's true all over the place. In fact, we're doing it right here. I'm defining a variable whose value is a lambda. This is nothing new, but I also can do that inside of a let or a let star. Presuming I don't try to use a variable inside of C, that's one of these earlier ones, then I need a let star in order to pull that off. What a let star won't let us do is it won't let us, for example, define a function that calls itself. Let rec, recursive, would allow me to like define the factorial function that keeps calling itself until it finally is the factorial of 1. You would need let rec to define a function that's defined in terms of itself in there. And we'll see an example of that at some point. But that's kind of the increasing, you could effectively say, I'm going to always use a let rec, now I'm covered. That is technically a truth. I would say good programming practices, you should use the least powerful tool that you need to use to accomplish what you're trying to accomplish for performance reasons. But what I just said is true. You always use a let rec, you're fine. Good. Yeah, and then it also allows you to have functions that call themselves defined in the environment. Homework. Add the ability to have let expressions into our language, where a let has a list of 2 lists, temporarily adding variables to our environment, and executing the body of the let in terms of that newly expanded environment. Shouldn't actually be too bad once you sit down and think through it. All right, questions, comments, concerns, bribes? Right here. Yeah, so I mean, if you want an example in our code, we can say something like ask less than 510, then let B2 C3 plus BC otherwise 10, something like that. So here's a function that defines a more local environment with a variable called B that's equal to 2, C that's equal to 3, and this is more local than whatever environment you're currently working with. And then it just does some math with B and C. So even if we had more global variables, B equals 14, C equals 35, this guy should boil down to a 5 because it's being done within this more local environment. So this is going to involve calling your extend D and B, more local versions of your stuff. All right, anything else? All right, I will see everybody on Tuesday.
Hey, Professor.
Oh, how was turnout in CS Club last night?
Not the best, but
So crap.
yeah.
Were you able to, did you connect with that one student?
Yeah, she messaged me.
Okay. Okay, cool.